So today we're going for interference of light. Okay. So have you seen this color shape? Actually, if you go to if you have oil on the surface of water, or you have a soapy balloon, you know the balloon when you make a balloon, soap balloon, water slung or a balloon. Okay, you can find that there will be this kind of pattern. Actually, this pattern is not because of the color of oil itself. It is because of the interference of the light is coming to your eye. The interference of the light that makes its color uh, blue. Some will be red, and some will be between that. Okay. So, an algae black oil spot and pavement can become a thin beauty after a rain, and the oil reflects a rainbow of colors. Multicolored reflection can also be on surface soap bubbles. Yeah, it's the bubble. I was searching the word for bubbles and DVDs. Okay. How is it possible for colors object to produce a remarkable colors in our discussion on lens, mirror, and optical instrument? So we're going to interference of light. Next, okay, the effect of superposition of two waves, constructive or destructive, is known as interference. Okay, this is what you have known since you are Form 4 and Form 5. The difference between two light sources can be observed. There are two conditions must be met. Okay, the source must be coherent. This is much most important thing. That is, the source must be coherent. This one, number one, and they have must have constant phase difference. If you remember in Form 5, what was the definition of coherence? What was the definition of coherence in Form 5 or Form 4? What was the definition of coherence? Can you put on the chat down there?
Two same sources, sir.
Hmm? In Form 4
Two
what?
same source.
Same source. Same source? Is it? It's only same
Yeah,
source.
same source.
Okay.
Two same source.
So want when you introduce when you are in Form STPM, you must have to say that you will be constant phase different because you already learned what is a phase different, right? Okay, phase different 15 aspect to each other. So phase different in the wave, you know that the phase different is how much the difference of the wave. Okay, when you have a, a phase diagram, you can see that how much is the phase difference between two wave. Okay, they call as phase different and respect to each other. Of course, the first wave and second wave, although they have a little bit difference, little difference at the time, but the phase difference are constant. The phase difference are constant. That's where the most important thing when we say about coherent source. The wave must have the same intensity or almost the same intensity. If the two wave sources are coherent, they always have the same phase difference between them. The interference pattern should be stable and observable because the position of nodes and antinodes will always be fixed. Thus, we'll be able to see them. If the two wave sources are incoherent, the interference pattern is not stable because the interference pattern will not be stable. So, it's either stable or not stable. If it's stable, you can see, remember the two light source. Okay, when you put on the two light source on the screen, if it was stable, we can see that it will be a dark fish. Dark fish for all the time, all the time. But if you are not stable, sometimes it will be dark fish, sometimes it will be a light fish, light fish. Okay, you can observe. So they cannot see where actually the interference happens. Okay, unless it is stable. Condition of two light current to be coherent must be have the same wavelength or frequency. Of course, when we have same wavelength frequency, then the what you call the phase difference will be constant throughout all the along. along the wavelength of two wavelength of the two wave. Two light sources must be originate from the same chromatic point source. Okay, chromatic means, why is it chromatic? What it means by chromatic? Who knows why is chromatic? Abi, Usha.
Color.
Yeah, same color, single color actually, yeah, single color. If usually in the lab we have a red laser because it's a red, one color, or we have a green laser. Okay, black. So black color, or say green or red laser, is the most common used laser in the lab. Okay, the light emitted by two bulbs, source number one and source number two in diagram below, source contain short pulses of wave. We are not current even if the frequencies are the same. Okay, you can see that. You can see that although both of them frequency and lambda are same, you can see that the phase difference is changing. So you cannot have a constructive or destructive, a stable constructive destructive point. One thing that is new to you we call this optical path difference. Optical path difference. So you can see it's actually meaning of the path of the two light is different. Optical path length of a light traveling is a definition of this. The optical path length of a light traveling in a medium is equivalent to the distance of the light would travel in vacuum. So there are two medium or two medium wave. One is a medium, one more is a vacuum. At the same time interval, if a light travel a distance L in the medium of refractive end of the optical path, the length in the medium is given by NL. N stands for uh, N stands for refractive medium over here, refractive medium. Okay, index of refractive medium, and L will be the distance the light travels. So actually, it is like this. We have one medium, let's say it's a glass, one medium over here is a vacuum. So light travels over here and light travels on the vacuum. So because we know that when the light travels in the medium, let's say medium is a glass, the light travels slowly, then the light travels medium. So we want to see how was the difference. This one is shorter and this one will be longer, right? Because when the light move in the vacuum will be very fast, right? The speed is like a 3 point something 3.0 10 power 9 10 power 8 10 power 9. Okay, in the vacuum the light travel very fast. When we enter in the medium, the light will be slower. So we want to see in this distance L how much it will be in distance L2. Okay, is to compare in the vacuum how far it can go and how far it can go to compare to how far it can go in the vacuum. So of course in the vacuum will be it must be much more longer. When it was in the gas, in the sorry, it's a gas in the glass, it will be much more shorter. It's not. It will be slower than inside the glass. So the proof is speed of light vacuum. Actually, this is not. I don't think it's a speed. The speed of light in the vacuum medium is given by C over N. Of course, C over N. How much the speed of the light divided by reflective index. So this is speed of light in medium, right? The speed divided by the N. Okay. Time taken travel through the medium is T over D over V. Of course, V equals to D over T. Correct not? So you have D over T as the equation title. So D over L over V. So the whole thing is L over here. The whole thing is L. So L is actually n times L because it is in number of refractive index, or can say that NL because it's inside the refractive index NL over C. Oh, for one more, here N L and C, C and T. Okay, so actually this part goes down over here, so we have N L over C. So actually it's 1 over T, right? 1 over T. I think this part is something wrong with that. It's 1 over T equals to C over L. And no, it's 1 over V. Yeah, it's 1 over V. Of course, it's V in the glass. So T equals to N L over C. Number of reactive index, different index. The how long is the medium L, and divided by C, the speed of the light. Okay. At the same timetable, the light in the vacuum will be have a travel of x equal to ct, okay, or equals to nl. Of course, n will be 1, right? 0. Is it? Or is it comparing ct in the vacuum and nl in the medium? Okay. So if n equals to 1.5, this is a reflecting index for a glass, and L will be 2 meter, means the glass is 2 meter, then the optical path length will be 1.5 times 2, so will be 3 meter. So it says that this is the same optical length travel at the vacuum for 3 meter because the time taken is same. So why it says that, by comparing, if we have 2 meter, okay, over here, so the light enters and goes to other side, and we have 3 meter, this is a vacuum, okay, light enters and goes to other side. Vacuum will take 3 meter from one point to one point. In the glass, it will take 2 meter from one point in the same time. This is the most important, that is same time. Vacuum, it takes 3 meter. For glass, it takes 2 meter. So you see that it can go faster in the vacuum. Of course, it's 3 meter. That's why we have a faster. And for the glass, it is only pass through meter in the glass. And one more is a constructive interference. What happened in the constructive interference? So we have two coherent wave source separated by distance for lambda. Okay, one source over here, a second source. The source over here, S1, over here, this is S1, is propagating, giving, we call it, emitting wave to the other side, to point B. Okay, as this one is actually is propagating to whole place of the surrounding, but actually we want to count at B only. Okay, so S1, okay, and one more, S1 and S2 is coherent, it must be coherent. S1, okay, is propagating to B, and S2 so is propagating to B. Both of them is coherent. Okay, what is different between them is the length. You see that S1, the length S1 to B and S2 to B is different. Okay, it's different because of optical path difference. So S1 to B and S2 to B, although is a coherent, but the path, optical path length, both of them is different. Okay, so because of the difference of optical path length, okay, if R2 optical path length, okay, minus R1 equals to m lambda, we will get a constructive interference. It means that it's either the crest will meet a crest, or a curve Okay, a trough will meet a trough. Okay, so there were two, either crest or crest we meet a crest, or trough will meet a trough. So we want to see the difference between them. In this case, we have over here S1 to B is 7 lambda. If you count 1 2 3 4 5 6 7, there will be 7 lambda. If you count R2 sine S source number 2 to B, there will be 9 lambda. So you count 1 2 3 4 5 6, there will be 9 lambda. So 7 minus 1 will be 2 lambda. 2 lambda is M lambda. So over here is actually M is 2. Okay, so you can see that M can be start from 0, it can be 1, it can be 2, it can be 3. Okay, so if the both of them, okay, as I conclude, both of them has the difference is M lambda, they will have a constructive interference. Okay, so it, because we are counting at the B, we count at the, if you measure at somewhere else, okay, let's say the other side over here, also constructive, this one also constructive, and this one also constructive. Okay, it depends, because when we minus R1 and R2, there will be difference of M lambda. Okay, any question about this one, this slide? Any question before I goes to destructive? Any question, anyone, before we go to destructive interference? If you okay, you type there okay. If you understood, you type there understood in the chat. Okay, now we goes to destructive interference. Destructive interference in other side. Okay, destructive interference in the other side. Let's say S1 and S2 go emit, both of them are emitting the wave, and we just want to measure at C. You see that S1 and S2, okay, both of them emit, but we just want to measure at C. The first uh, I mean uh, I mean that source number 1, the wavelength is 9.75 lambda. It means that if you count 1 2 3 4 5 6 7 8 9, it will be 9.5 lambda at this point. If you come from source number 2, you measure 1 2 3 4 5 6 7, it will come with 7.25 lambda at C. So both of them have a collision, I mean they overlap at the C. If they overlap with M lambda, M plus half lambda means that it has 0.5. Okay, it's easy to say that it has 0.5 lambda. Okay, so both of them has 0.5 lambda in the different, because you see R2 minus R1, 0.5 lambda. It means either a crest overlap with a trough, or trough overlap with a crest. Okay, then we have a destructive interference. The lambda, okay, there are two sides. If you want to minus or you want to plus. If you want to minus, it start with 1. You see, if you start with plus, we have to start with 0. Okay, actually the same thing, right? Minus or plus. Minus half, minus half, start with number 1. Plus 1, start with 0. Actually the same thing, right? Either you start with 0, or either you start with 1. Either you plus with 1 over 2 is over here, or you start with 1, you minus 1 over 2, also it goes back to the same place. Why not? So don't make you confused. Okay, so for destructive interference, you see that it must be half lambda overlap. Both of them, if you minus R1 and R2, you have 0.5 difference. When you have a 0.5 difference, it means that the crest is overlapping with the trough, or trough is overlapping with the crest. Okay, any question at this point? Any question? So you see, actually it is not, it is not, uh, it is not we just count a measure as C actually. Actually, it happens at this point, every this point. Okay, it's because of the both of the overlap of the wave are plus or minus 1 over 2 lambda. Okay, can I go to next slide? Can I go to
Yes,
next
sir.
slide? Okay. How about Keshika? Keshika, do you understood? Sometimes I like to ask Keshika. Keshika, do you understood what's happening in front? Keshika?
Yes, teacher.
Okay. For constructive interference, what will be the formula? R1 minus R2. Keshika. For constructive interference, R1 minus R2 will be equals to
So is it the n plus 1 over 2 lambda, sir?
no constructive. Keshika,
2 lambda,
constructive.
right, sir? 2
Constructive.
lambda, right, sir?
It's
2
not
lambda,
two.
right?
It's m lambda. Yeah, it's m lambda.
Okay.
Okay. So for constructive, I repeat, for constructive interference, R1, the first the first wave, first length, actually we call this optical path R1 minus the second optical path R2 equals to m lambda. This is for constructive. M can be 0. Yeah, is it 0? It can be 0. It can be 0. It can be 1. It can be 2, and so on. This is for constructive. So in previous example, it happens that R1 minus R2 equals to 2. It means that M is 2. It happens also if M is 1. If M is 1, both of them minus M is 1. It also happens. Okay. So 1, 2, 3, and 4, and so on. If destructive interference R1 minus R2, it means that both of the wave, when you minus the optical path length, you have m plus 1 over 2 lambda. It means that the difference of between them is 0.5, half. You see, if you minus, let's say we have a wave here, Cassandra. If you minus or you add up with like this is half of it, means that is half. Let's say this one, I make one more, and then this one goes up and down and up again. Okay, can see that this is, you minus these two, this one and this one, you minus both of them, you get 1 over 2 lambda. You got 1 1 2 2 lambda as a result of minus these two. It means that they have actually a crest, a trough overlapping with the crest. So that's why we have a destructive interference. Okay, that's why you have it. Understood, everyone? Do you understood? It's very difficult to explain actually. Any question before I proceed? No. Okay. So for this example, in diagram shown, P is a point in middle of the screen. P is a point in middle of the screen. S1 and S2 are coherent. S1 over here and S2 are coherent, which is in phase. because coherent of course is based a thin film of refractive index n and thickness T is placed in front of S1. So what happened is at the S1 over here we put a glass, okay, a glass or thin film with a thickness of T, very small thin film. Derive optical path difference between the sources at point P. So how much S1P minus S2P. So optical path difference equals to S1P minus S2P. How much is it? The first question. Second, what is the condition for dark phase to be formed at P? Dark phase to be formed at P, it means that there are no light at the P there. At this point, there are no light. When it happens at the P, it must be destructive interference. So destructive interference will be S1P minus S2P equals to M plus 1 over 2 lambda. It must be different of them must be M plus or minus 1 over 2 lambda. It must be 0.5 lambda will be different. Given number C, given that n equals to 1.50, so it given you how much the reflective index over here, n equals 1.50 and lambda equals to 6.80 nanometer. Calculate the minimum thickness of the film so dark phase is formed at P. Okay, now it given you this n, it given you the lambda of the wavelength. Find out how much the thickness of this thing, okay, to be formed. The question to be formed at P. Okay, now number 1, S1P equals to S2P equals to L. So you can say that this L and this L actually are same. Okay, so optical path difference. Okay, optical path difference. S1P minus S2P. S1P is this point. You see, this is S1P. This whole thing is S1P. Why? Because you see L minus T. So this L minus T. L, the big L minus this T. Very small T. Okay, times 1. Okay, times 1 plus NT. What is plus 1? This is anything about plus 1 times 1 plus T. This is say what? 1 meter. Is right? Refractive index. Didn't say anything. Okay, LT times 1 plus with NT. NT is actually inside. NT is inside the glass. Okay, so you see it goes outside and then it goes inside with NT as the optical path and then goes back to outside. So that's why LT is L, okay, and then minus T, and then we calculate add up with NT inside minus L, as L is actually as source number 2 times with the P. So NT minus T, and then you have N minus 1T. Okay, this is optical path difference between source number 1 and source number 2. N minus 1 times with the T. Okay, the second question. For destructive interference, optical path difference will be X equals to M minus 1 over 2 lambda. So M can be 1, 2 and 3. This is very basic. Okay, to happen to be dark phase, to happen at P, it must be X. I mean the optical path difference since source number 1 P and source number 2 P must be M minus 1 over 2 lambda. Number 3, what will be the thickness of this thing if P is dark phase? So X minus equals to 1 over 2 lambda, taken M1 for minimum thickness. Okay, so it can be M1, it can be order of M2, it can be order M3 and M4, but we take M1 for minimum thickness. Okay, so x equals to 1 over 2 lambda n minus 1. Remember the one we derived together, the answer for A. This one answer came from A. N minus 1 t, the optical path difference between source number 1 to P and source number 2 to P is n minus 1 times t equals to 1 over 2 lambda. So 1 over 1.5 minus 1 times t, 1 over 2 times with the lambda. This is number of lambda. So t over here, exactly the t over here is 6.80 times 10 power negative 7 meter. Then this p will be a dark fish. Okay, then it will be the dark fish. If it's other than this number, it will not be. You can also change m to m, substitute m as 2, and also can substitute m as 3. Also you can get the value of t as a dark fish. So there will be different of answer. Can be this is when m equals to 1, m equals to 2, there will be different, and m equals to 3, there will be different answer. Okay, any question? I'm going to stop here actually. Any more? Oh. Any question? Anyone?
No, sir.
No.
I think so far so good, sir.
So far so good. Okay. So
Yes,
actually
sir.
we have a running out time of Zoom. We have 1 more minute. Any question? Faster, in 1 minute. Cherry said easy peasy. Okay.
So normally, what's the question they ask in where they ask normally they ask essay question for light or what, sir?
It can be usually it's like in this kind of question, it will not be a question in the structure. Usually it's in the essay.
Oh.
Much more marks can be given in the essay.
Okay, sir.
So any more question?
No, sir.
Okay, so I'm going to stop here. Tomorrow we have a class, right? We have a class tomorrow.
Yes, sir.
Okay, so tomorrow we see you
Yes,
tomorrow. Huh? We have class or not?
Yes, sir. Every day got class, sir.
Every day. Okay.
Yes, sir.
Okay, so see you tomorrow with the next lesson.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Okay. Come.
Thank you, sir.